Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon to all of you. Okay, so how are you today? Ada yang affected on the heavy rain 2 days? I think maybe some of you got affected by that heavy downpour in Klang and Shah Alam. Okay. Yeah, because my sister also stayed in Klang, and her house is actually has been drawn paras pinggang very very tinggi jugalah dia punya level of the flood tu. Okay, so okay, I think just straightforward go to our class today. So for your information, um, for the AC nodes, okay, for the AC circuit analysis, majority of my videos will be not following the slides, okay, because actually for the AC circuit, I think I have mentioned in previous class, the same methods, the same concepts, okay. We will actually go through back the basic Ohm's law, the nodal analysis, the mesh analysis, Thevenin, Norton theorems, superposition theorem, but actually the same, but in where we involve complex numbers. Okay, so that is the difference, where we have a complex numbers, the Phasor diagrams, and so on. Okay, so I will not follow the slides. Okay, on my videos. Okay, so let's start with the one example exercise from the Sadiko textbook. 9.28. 9.29 you can ignore because this one is actually out of your syllabus. Okay, out of your syllabus. So please concentrate on 9.28, 9.3, and 9.31. Okay, let's first go to the 9.28. So determine the current that flows through an 20 ohm resistor connected to a voltage source. So if you don't have, um, you can redraw the circuits. Okay, so as mentioned in the pre-recorded video that I hope you have watched it. Okay, so all the AC circuit analysis will be in phasor domain. Phasor domain, or sometimes also we call frequency domain. Okay, we are not analyzing our circuit in time domain. So we are actually analyze our circuit in phasor domain, or also known as a frequency domain. Okay, so right now you need to convert first. Okay, you need to redraw the circuit in a phasor circuit, phasor equivalent circuit. Okay, so the load is resistor 20 ohm, so it is already a real number, so 20 ohm. Okay, and the voltage you need to change into a phasor domain. So your Vs, capital letter. So in phasor, we only concentrate on the magnitude and the phase, which is 37 degrees. Okay. And so from here, you can see, you can calculate the current. Okay, this is the question, calculate the current. Okay, so from here, so this is a very simple circuit. So your I is equals to V over R. So right now your V is a Vs, okay, because this one is V. So 120, 37 degrees, 20 ohm. I think you should get around maybe 6 with a 37 degrees current. Okay, but this one is still not complete yet. Since it give you in a time domain, so you need to convert your value of current in time domain. So this one is a phasor domain. So your time domain equivalent, so this is I 37 degrees amperes. So your time domain is IT, the magnitude is 6, and the function used here is cos. Okay, so just follow cos, and the omega is 3773. Okay, 3773 plus 37 degrees ampere. So this is your time domain answer. Okay. Okay, so if you draw the phasor diagram, uh, what I call, I think phasor diagram. Okay, we call that phasor diagram. Where to draw? I think we draw here. If you are required to draw a phasor diagram of V and I, so you should draw like this. So V, so this is your imaginary part, and this is your real part. Okay, so your voltage here, which is Vs, 120 with an angle of 37 degrees. So this one is 37 degrees. Okay, and your current is this one. Since this is the load, okay, resistor, so meaning that the voltage and current are in phase. So your current is also with an angle of 37 degrees. Okay. So I hope you have already watched my pre-recorded video, the relationship of the voltage and current for different type of load. So if you have a resistor load, your V and I are in phase. In phase, meaning that there is no phase difference between the voltage across the resistor and the current that flow inside the resistor. Okay, so V and R are in phase, as shown in this phasor diagram here. Okay, but when your load, okay, your load is a capacitor load, okay, where this one is your voltage and this one is your current, so VC, and then this is IC. So please bear in mind that for this kind of load, okay, I think current is leading the voltage by 90 degrees. Okay, meaning that if you draw the phasor diagram, so you can just show that this is the current and this is the voltage. Okay, the current is leading the voltage by 90 degrees. Okay, and if your load is a inductive load, inductor load, so this one is your RL, this one is your VL. So the current is lagging voltage by 90 degrees. So if you are draw here, so meaning that your current, maybe this one is your voltage, and this is your current. Okay, so the current is actually lagging the voltage by 90 degrees. Okay, this one. But if you have a combination of a load, for example, if you have a resistor and resistor and inductor R and L, so this one we call inductive load. Okay, inductive load. And if you have a resistor and a capacitor, so this one we call capacitive load. Okay, this one is pure resistor load. This one is pure capacitor load. And this one is pure inductor load. So for example, and then if you have a combination of R and L, so we call this one as an inductive load because it has inductor effect here. So that's why you call inductive load. And if you have R and C, so this one we call capacitive load. And the relationship between the voltage across the load and the current is depends on the angle. Okay, so right now as you can see, the current is leading for the pure capacitor, the current is leading by 90 degrees. Okay, but when you have this kind of load combinations, so it is actually up to the uh, type, if it's actually up to the values of the inductor to determine the angle. But this one inductive load, the current will always lagging voltage. For capacitive load, the current will always leading the voltage. Okay, but the angle is not 90 degrees. Okay, the angle is determined the value of the what you call the impedance. This is what you call impedance. So for this one, the impedance is R plus J omega L. And for this one, the impedance is R negative J 1 over omega C. Okay. So for inductive load, the current will always lagging the voltage, but the angle is not 90 degrees. It depends on the values of the impedance angle. Okay. Because after this, you have this one is Z with a magnitude of theta Z. Right. And this one, the impedance is Z is equal to Z with an impedance of negative theta Z. Okay, so for the capacitive load, your impedance angle will be negative. For inductive load, your impedance angle will be positive. Okay?
Doctor,
Yeah.
for the for the for the inductor one, you said that the current is lagging voltage by 90 degrees, right?
Sorry? You
For
mean
the
for
inductor,
pure inductor?
yes, pure inductor. Right.
Yeah. For pure inductor, yes, the current is lagging.
Doctor, if we do we calculate the angle by anti-clockwise or clockwise?
Oh,
Because if you saw here, Doctor, you used anti-clockwise to measure the angle, and for the
no,
second one, you
actually,
used
the phaser, you put your eyes here, so the phaser is actually running anti-clockwise actually. Okay, so meaning that, for example, if you put your eyes here, okay, the rotation is actually anti-clockwise. So what you see first, the current or the voltage first?
the voltage.
Huh?
The voltage.
No, current. You will see the current is always first.
The capacitor or the inductor?
For the inductor, yes. For the inductor, yes, the voltage. You will see the
Yeah, okay.
voltage first.
Yeah, yeah,
So
okay.
then after that current. For the capacitor, you will see the current first and then after that voltage. So that's why for the pure capacitor load, the current will always leading the voltage by 90 degrees. And for the inductor, the current will actually always behind the voltage by 90 degrees. Okay.
Okay,
I hope
doctor.
you that one clarify your understanding.
Yes, doctor. Yeah.
Okay, thank you very much for your questions.
Welcome.
Okay, this is a fundamental component that you need to know. Okay, the relationship between the current and the voltage across the loads. Okay. Okay, so this is actually has been explained in my pre-recorded videos. So I just want to maybe refresh again. Okay, let's move on the second example, which is 9.30. Oops. Actually, this Microsoft Whiteboard, they have actually revert back to the original version, which is very good. Okay, so 9.30. Okay, so right now you have a voltage is applied to a parallel combination of 40 kilo ohm resistor and 50 microfarad capacitor. Find the steady state current through the. Okay, so right now the circuit, you can imagine the circuit is like this. Resistor and capacitor are connected in parallel. Okay, and then a voltage applied, meaning that the voltage here, this one is VT. The voltage is applied to a parallel combination, meaning that the same voltage will be at cap resistor and also capacitor. Okay, the same voltage, which is 100 cos 60t plus 20 voltage. So it is actually just like you have a voltage supply, okay, which is has that values VT is equal to 100 cos 60t plus 20. So once again, yes, you need to redraw the circuit in a phasor domain, okay, in the phasor equivalent circuit. So your capacitor, so R is R, so you just put the value of your resistor. So you don't need to convert into because for R in time domain and phasor domain is actually the same, which is 40 kilo ohm. But for the capacitor, you need to calculate what we call reactance. So X is actually reactance. Okay. So what is X? So we have a capacitor Xc, which is negative J 1 over omega C. Or sometimes also you will see in the maybe YouTube channels or maybe YouTube video, Xc is also 1 over J omega C. But please don't confuse because J here is actually at the bottom part. If you want to remove to make the J is at the upper side, you need to put negative sign. So negative J omega C. That's why we have negative J 1 over omega C. Okay? So Xc is negative J 1 over omega C, and we have another one which is we call reactance for the inductor, which is positive J omega L. Okay? So right now your Xc is so you need to calculate negative J 1 over omega C. So negative J, so 1 over, so right now your omega is actually your angular frequency, angular speed or angular velocity, which is given by the voltage source. Okay, so if the voltage source is 6t, so meaning that all the elements are actually operated at the same omega. Okay, so for this circuit, you need to operate in one single omega. So that's why when you have a voltage source, omega is 60, meaning that all the elements are operated at the same angular frequency. So 60 multiplied with the capacitor values, 50 microfarad. So this one will give you negative berapa 60 multiplied with 50 exponential negative 6. Okay, and then invert. So you will have negative 333 ohm. Okay, so negative J333 ohm. So the unit is ohm for the reactance. Okay, the unit for the resistor is also ohm. So actually all the units are in ohms. Okay, so it's okay. Okay, that is why we need to convert into X. Okay, because X, the unit is ohm. So right now, the voltage source also you need to convert into its phasor domain. So we have capital V. The magnitude is 100 and the phase is actually 20 degrees. Okay, so if you want to draw the phasor diagram, so meaning that your voltage is actually here, voltage 120 degrees. So this one is your 20 degrees. Okay, this is 0 degrees. Okay, the rotation is like this, anti-clockwise. Okay, so the question wants you to find the steady state current through the resistor and capacitor. So since resistor and capacitor are in parallel, so meaning that you can calculate directly the current. So this one is I1 and this one is I2. Okay, so your I1, yeah, very simple right now. This is a phasor domain, so V over R. 100 over 20 over 40K. So you should get the same, you should get actually 100, okay, with an angle of 20 over 40K. Okay, so it will give you the values in rectangular form. So you need to convert, you can convert into a phasor form, polar form, sorry, polar. So you should get the value is 2.5 milli, okay, with an angle of 20 degrees, okay. So 20 degrees. Why 20 degrees? Because as you can see, this is a resistor. So meaning that the voltage across the resistor is in phase with the current that flow inside the resistor. So this one, please don't forget milliampere, okay? Because some of the previous student they calculate it, but they miss to put milli here. Okay, so it will make your final answer incorrect. So milliamperes. So if you want to draw the current, so the current will be in, I think milli, 2.5 milli. So this is your current. Okay, it's up to you to put the values or not. Okay, so this is your I1. Sorry, this one is your I1. Okay, so it is in phase with the voltage. It is in phase with the voltage source, okay? Because this is a parallel. So, okay, I hope you got what I mean. And then next is I2. So your I2, so V over XC. Don't put V over C. Okay? V over XC because right now this is the reactance, not capacitor. So there's a difference because capacitor is farad. Unit is farad. And the reactance is ohms. Okay, V over XC. Don't put V over C.
Yeah,
Okay?
why, Doctor, why we use reactance, not capacitor?
Okay, why? Oh, that one is a very good question. Okay, so right now, actually, the capacitor, as you can see here, if you have, I think I have explained, for example, okay, let me show you. So this one is VT, 100 cos 10 T plus 20 degree, for example. Oh, quite long. Okay, you have resistor. Tak nak lah. Quite difficult. Example. You have a resistor connected in series with a capacitor. So resistor, for example, this one I put maybe 5 ohm. And my capacitor is 20 millifarad. Okay, can you calculate for me what is the current? It's quite difficult, right? Because right now, the unit is ohm and this unit is farad. So you cannot mix the units Okay, you need to have a standard, you what call your unity units. The unit is the same. Okay, so this one is farad and this one is ohm. So you cannot what you call try to have this solved by using a different units. So what we do in time domain is actually we need to have the voltage here, the VR and also the VC, right? So the VR is actually straightforward. IT multiply with the R because R is a constant. Okay. But the capacitor is quite difficult because what is the relationship between the voltage and the current of the capacitor?
Still, we don't know.
IC is what? IC is one. What is it? What is the voltage? Okay. The voltage. The voltage capacitor is 1 over C IC. The integration. Okay, the integration 1 over C and then integration of ICT. So which is very difficult because if we want to use this time domain, so it's quite difficult. Okay, so what we
It
do,
will take for long.
yeah, it takes too long to analyze this very simple circuit. So what we do is actually to convert it into a phasor where we have this capacitor represented by what we call the reactance. And this unit reactance is actually ohm, which is similar units with the resistor. So if you have the same units, okay, then you can solve it by using a very simple, straightforward, complex numbers. Okay.
Okay.
Okay. So right now,
Doctor, can we just use C
sorry,
times dV by dt?
sorry, you can get
I
IC
is
is
equal
actually
to
C
C
dV
times
dt.
dV by dt.
Yeah. Yes. But still, you need to have the differentiation. Okay. IC is actually C dV dt, right? You need to differentiate dV dt, the voltage across the capacitor. So right now, the voltage across the capacitor, you don't know. It is unknown. Right?
It's
That's
given,
why.
right? The 100 cos 60.
No. That 100 here is actually your voltage source.
Oh, okay.
Maybe you can use VCT is actually maybe you use a voltage division, but it's still quite difficult because you need to know because this you cannot use the voltage division also because the unit is different. This one is farad. This one is ohm.
Yeah, doctor, I understand you. Like as if we want to add x plus y, we can't add x plus y.
Sorry?
Never mind, doctor.
Ah,
Never
okay,
mind.
okay. Okay, so you see the complexity if you are using the time domain. Okay, because if in the AC circuit, if the circuit contain only resistor, then it's straightforward. You can use time domain and whatever. Okay, but when you dealing with non-linear elements, the storage element, which is the inductor and capacitor, the relationship between the voltage and current are not linear. It is actually, for example, the voltage across the inductor is actually L di over dt. Okay, and for the VC is actually I 1 over C IC. So the integration. So it's quite difficult to actually to analyze. So what we do is actually to transform them into a phasor domain that very easy lah. Okay, easier to analyze. Okay. So when you have transformed into the phasor domain, you can use all the DC analysis concept. Okay, the concept that you have used in the DC circuit into AC circuit. If you are using time domain, you cannot apply all the concepts, all the methods that you have learned in DC circuit, apply in AC circuit. You cannot use that. Okay, if you are using time domain. Okay, for example, the voltage division you cannot use directly because this you need to have a very complicated conversion. Okay, you cannot use, for example, VC. You use voltage division. You cannot use that. Okay, unless you convert it into a phasor domain circuit, which is you need to convert the C into XC. Okay, and then after you have converted that into a phasor domain, then you can use all the theories that you have used in DC circuits. Okay, so we continue. So 120 ohms. So this one is negative J333. So this one is actually 120 degrees. So this one, negative J333, is actually, if I convert into a polar form, is actually negative 90 degrees. Okay. So this one, 100, the magnitude 100 over 333. So it will become 0.3. And the angle is 20. Negative 20, negative 90. If you put back at the upper side, it will become positive 90 degrees. So this one is 0.3110 ampere. Okay, so if you want to draw the phasor of I2, okay, so 110 mean that this one is actually here. 110, so this is your I2. Okay.
Doctor,
Yes.
for the answer, can we just leave in a fraction?
What do you mean by fraction?
Like I just write 100 over 333 and then I write the angle.
Oh, I think it's better to put, you solve the fraction. It's much easier.
Oh,
You solve the fraction.
okay.
Okay. Okay. So, usually if the question give you the voltage in time domain, the final answer should be converted back in time domain. So meaning that this is the phasor answer. So your I1 in time domain is 2.5, and the function, you need to look at the function. What is the function used for the voltage source? So the function used is cos, and the omega is 60. So just follow cos, and the omega should be the same with the voltage source. So 60 T, and the angle is 20. So plus 20, and please don't forget milliampere, because when you calculate it, this is milliamperes. And for I2, so this one 0.3 cos, the omega is still the same, 60T plus 1103 ampere. So that is the final answer. Okay, because one circuit only have one omega. You cannot have one circuit have multiple omega values. Okay, so if the voltage source give you this information, mean that all the circuits will operated at the same omega. The only difference is actually on the phase, because this phase is actually depends on the loads and so on. For example, if you have like this, right? Okay, capacitor and resistor and so on. The omega is still remain the same inside one circuit. Okay. So next, we move to the last one. Actually, I have pre-recorded, I think 3 examples. Okay, from I think one of the question from the previous final exam. So I have already shared just now the pre-recorded video in my YouTube channel. After this, you can watch it. Okay, maybe you can just snapshot the question first, and then try to do it by yourself, and then maybe you can just check the answer through the videos. Okay, because I have because I haven't saved the solution in Word document. Yeah, I forgot to save it. Okay, so 9.31. So I hope you still following me. Okay. So because this subject is like some mathematics lah. Okay, you need to do the exercise and so on. Okay. Do we have anything in the chat room? Okay, because sometimes when I haven't checked the chat room. Okay.
Doctor?
Yeah.
So if like just now the question like arrange in parallel, all the current must calculate separately, right?
It depends on the question.
Okay.
It depends on the questions. Okay.
Is that possible? Like the first row is a resistor, and then second is a capacitor and resistor in series.
Yes, possible.
Okay. Thank you,
Yes,
Doctor.
possible. Okay. I think yes. I think I have one example on that because I got what you mean. For example, you have like this voltage source, and then you have a resistor, and then you have a combination of resistor and inductor. Yes, you have R here, and then you have XL here. Then calculate what is your current here. Yes, it's possible to have this kind of questions. Okay. Maybe after this, I will show you one simple example on that. Okay. Series. This one is very simple, straightforward. This one is parallel, and then 9.31. 9.31 is series. Okay, and then if the input voltage is given, okay, so right now, so you have like this. Sometimes I write down sinusoidal, sometimes I put positive negative. It's actually not a big deal. So R, L, and also capacitor. Okay, so what you need to do is to redraw this into its equivalent phasor circuit. So R, so directly put the values R, but the inductor XL you need to calculate, and also the XC. So XL is J omega L, while XC is negative J 1 over omega C. So calculate. And the voltage here, okay, so the phasor domain of the voltage is 115 with an angle of 0. Okay, 0 degree. There is no phase. This one is omega. Okay, so J 2, omega is 2, multiply with the inductor value, millihenry. And this one is negative J 1 over 2, multiply with the capacitor value 5 millifarad. So what is the values? So this one 240 milli multiply with 2, so 0.48. So 0.48, and the capacitor value is 2 multiply with 5 sorry, this one is micro, oh milli, sorry, 2 multiply with 5 milli, 0.01. Oh, 0.01 invert. So this one is negative. Is it negative?
Negative 100.
Okay, 100, right? Okay, negative J 100. Oh, quite big difference. This one negative J 100. This one 0.48.
Yeah, XL is 0.48, correct.
0.48. Okay, thank you very much for the double checking. Okay, so right now, calculate the current. So actually, this circuit, okay, if for me, I
Doctor,
put
we should put milli because We
Oh,
should
this one 240
or no?
milli multiply with 2. Yeah, 0.48 ohm, no milli.
Okay. Okay.
Okay, this one is ohm. Okay, actually, this one is impedance, which is R plus JXL plus XC, right? So R is actually 80 ohm plus JXL is 0.48 and XC is, oh, sorry, this one I think this one tak boleh lah. I think this one takut you confuse. This one positive JXL, negative JXC, right? So this one, if you calculate, so 0.48 minus 100. So you should get your J is negative, your total J is negative 99.52 ohm. Okay lah, so right now it makes sense because R is 80 and your reactant is 99, so makes sense. So can from here you can convert into this one is a rectangular form. You can convert into a polar form. So for 80 minus 99.52 I, and then I hope you can use your calculator. Okay, I hope you are able to use your calculator. Okay, you can try now. 80 minus 99.52 I, and then convert into a polar form. So it will give you the value. So right now, this is actually your Z in polar form. 127.69 with an angle of negative 51.2 ohm. So actually from here, you can know what type of this load. Is it inductive load or is it capacitive load? Can someone give me the answer? What type of load right now? So right now it's actually the combination of R and the reactance. Okay, but from this sign, the total reactant, from this sign, you can actually give me what is actually the type of the load. Is it inductive or capacitive?
Capacitive load.
Yeah, capacitive. You need to say capacitive load. You don't say capacitor load. If the capacitor mean that the load is a single capacitor, that is wrong. Okay, so actually this one what we call is actually the load is actually capacitive load. Capacitive. It's not. It's actually a capacity, meaning that it has a combination of resistor and capacitor. So meaning that the effect is a capacitive effect. Meaning that, what we mean by capacitive effect? Meaning that the current leading. Yes, that is the main part that we want to extract from this information. So if your load is a capacitive, meaning that the current will always leading the voltage. Okay, but the angle we don't know. The angle is depends on this one. Okay, so I will lead the voltage by 51.2 degrees. Okay, that is why. If your load is a pure capacitor, meaning the current will always leading the voltage by 90 degrees. But right now, the load is a combination of R and also reactance. So it is no longer 90 degrees. So, but it will lead, but the angle will be reduced. Okay, it depends on the values of R and also your X. Okay. Okay, so right now, this one, so directly you have the current V over Z. So your V is 115 with an angle of 0, and the impedance is 127.69 with an angle of negative 51.2 degrees. So this one, the magnitude 115 over 127.69, you should get 0.9, and the angle is when you want to put negative 51.2, so the sign will become positive, will be inverted, okay? So right now, if you want, we have the current, so you can put back the current in the time domain. So your IT is 0.9. The function of the voltage source is cos. Okay, so cos, and the omega is 2t. Sorry, the omega is 2. So 2t plus 51.2 degrees. So this is your answer in time domain. And if you are required to plot the phasor diagram between voltage source and current source, so this one is your current source. So just use this one, the voltage. Okay, so your voltage is actually here because the phase is 0, right? The phase is 0. If you look at back, so the phase is 0. Okay, the magnitude is 115 voltage, and the current is here. So the current is 0.9. I think much shorter, I think, because this one 115. So the current should be shorter. So 0.9. And the angle is 51.2. So right now, as you can see, the current is leading the voltage, which is, you should know that when you have this load capacity, meaning that, oh, my answer should have my current is leading the voltage. Okay, so that one is actually double confirm your expectation on the answer. Okay. Okay. So any questions before we proceed to the, I think, last question, that maybe the involvement of different combination of resistor, capacitor, and so on. Okay, so if there is no question, then I think we move to the, I think that's a very simple question. So this one, we have already this one resistor. Okay, and then you have this one resistor and inductor. So this one has been already converted into a phasor circuit. So your V is, for example, this one is 5, the with angle of 0. This one is 5 ohm. This one is also 5 ohm. And this one inductor is J10, for example. Okay, J10. So right now, can you calculate for me the voltage Vx? Okay, the voltage Vx. The voltage Vx is actually the voltage across impedance R plus J10. So, sama lah, Vx. So, from here, you can directly get, yeah, right, Vx is Vs. Because that one is parallel, right? Right? So actually, if you convert it into a phasor domain, you can apply all the analysis technique that you have applied in the DC circuit. Okay, and then next is current. Okay, so right now, calculate the current I2. So from here, you can just use I2. You know that I2 is Vx over Z, which is 5, 0. The Z is 5 plus J10. Okay.
Doctor?
Yeah.
How is the voltage for 5 resist?
For this one. This one.
For this one, for the yeah, it is as voltage source.
Yes, yes, correct. Yes. Meaning that the voltage, this one, V5 ohm here, is also Vs.
Yeah, how, doctor? We should first do the parallel one and find the R equivalence, so it is equal to the voltage source, right? Or,
I don't get what do you mean. Actually, as you can see here, it's actually the same principle that we have applied in DC circuit. So you see that this 5 ohm is actually parallel with voltage source, right? So that's why voltage, your voltage here is similar with the voltage source.
okay, doctor. Okay.
And this Vx is actually the whole voltage drop across this whole impedance. So the Vx is also is Vs.
Okay, doctor.
Okay. Maybe if you need some clarification, maybe you can just message me personally.
Okay.
Okay, I will do the best as I can to clarify that. So for example, and then
Thank you.
I1, sorry, not I1. I think this one I source. So what is your I source? So I source, yes, you need to have equivalent impedance, Z equivalent, right? Like macam it's like a previous one, R equivalent. Okay, for example, if you have voltage DC, you have this resistor, you have this kind of resistor, right? Oh, macam-macam lah resistor kan. You have this one, and then so calculate what is IS. So you need to calculate. You need to have this all simplified, right, to get R equivalent, right? To get the IS. Then after that, your IS is actually Vs over R equivalent, right? The same things can be applied in this circuit. Okay, so meaning that your IS is your Vs over Z. Right now is Z equivalent because it is a combination of resistor and also reactance. Okay, so what you need to do is actually to have the Z equivalent. So Z equivalent is, okay, sees from this point. Okay, so 5 ohm, so 5 ohm and J 10 ohm. So this one is, you can see your Z equivalent is 1 over 5. Sorry. For me, it's easier for me to just put a block here. So this one represent the impedance, which is 5 plus J10. Okay, so your Z equivalent is actually called 5 multiply with 5 plus J10 over 5 plus 5 plus J10, right? It's like you have a R equivalent, right? R1 and R2. So your R equivalent, okay, if you refer back to the DC circuit, so your R equivalent is actually R1 multiplied with R2 over R1 plus R2, right? So it's same. Okay. So this first element multiplied with the second element, and then over the addition of the first and the second element. So that's why we need to convert into a Phasor domain, because we can use all the methods, the theorems and analysis method to actually solve the problem. Okay. And then next, maybe the question can be, for example, after you get Vx, what is the voltage VR here? We call this one VR, for example. So you can use voltage division technique. So after you obtain Vx, so Vx is Vs, which is 5. So your VR uses a voltage division technique, which is resistor, the resistor, the element here, over the total elements, 5 plus J10 multiply with the Vx. So you can get your VR. Okay. Okay, I think from here I have spot one good example. Okay, for example, I have this voltage source, and then I have a resistor and also inductor connected in series. Okay, so this one is 5 ohm, and this one is J 10 ohm. This one, I think maybe V is equals to 10 with an angle of 0 degrees. Okay, so calculate the current. So from here, you can just calculate V over Z. Okay, so 10 with an angle of 0. Z is 5 plus J10. So this one, 10 and an angle of 0 over 5 plus 10i. Okay, convert into polar form. So 0.89 with an angle of negative 63.4. Okay. So right now, if you are being required, sketch Phasor diagram between Vs, this one is Vs and Is. Okay, I hope you can answer that, and then sketch this one, Vr, this one is Vl, for example. Okay, sketch Phasor diagram between Vr and IR. Sorry, this one is IS lah. And then C, sketch Phasor diagram between VL and IS. So this is a very interesting question, okay, to discuss. Okay, so right now, so let's see the first question. Sketch the Phasor diagram between Vs and Is. So Is has been calculated here. This one is your Is, V over Z. So if you are required to plot so this one is your Phasor plane. So your Vs is this one, 10 with an angle of 0. Okay. And then your current Is, so I think just put this one is just a Vs lah for simplicity. So Vs, and your Is is, okay, this one is your Is. As you can see, this one is negative 63.4. Okay, so actually going backward, negative 63.4. Okay, so as you can see, the load is inductive load. Okay, directly, you obviously you can see that it is inductive load, and you know that when it is inductive, so the relationship between Is and Vs, due to this load, it will have the current will always lagging the voltage. So right now, as you can see, we have shown you that the current is actually lagging the voltage by negative 63.4 degrees. Okay. Okay, that one I think straightforward. The second question is quite tricky, but it's actually, if you have a good fundamental, then it is very easy actually. So right now, sketch the Phasor diagram between the VR and IS. Okay, VR and IS. So right now, you can calculate your VR. So your VR is I multiply with the resistor value, right? VR. So your current is 0.89 with an angle of negative 633.4 multiply with the resistor value, which is 5 ohm. So you should get your VR is 0.89 multiplied with 5, so 4.45 volt with an angle of negative 63.4 volt. Okay, so right now, if I plot my VR, so my VR will be here. Okay, negative 63.4. And my current, the current that flow inside the actually IS is actually same, at the same phase. Okay, but the magnitude is different, 0.89. Okay, 0.89. Okay, so as you can see, the relationship of the voltage and the current for resistor is still applied. Okay, as you can see, the voltage and current that flow inside a resistor are still is actually in phase, which is same as what we have learned before this. Okay, so the voltage and current across the resistor is in phase. This one what we call in phase. There is no phase difference. It's in phase. Okay. Okay. So now, do you understand this one? Okay. So if okay, then we proceed with the next question, which is C. The sketch phasor diagram of VL and also IL. Sorry, VL and also IS. So, but firstly, what you need to do is to calculate the VL. So VL is I multiply with XL. I multiply with XL. Okay. So your current is 0.89 with an angle of negative 63.4. And your XL is 10. J is positive 90 degrees. So this one is 8.9 with an angle of 90 minus 36.4. Berapa So 90 minus 36.4. So you got 53.6.
Doctor,
Yeah.
isn't the current is 63.4?
Current. Oh, okay. sorry. Sorry. This one's 90. So negative 63.4. Thank you very much. So you should get 90 minus 63.4. So 26.6. Okay, that is your VL. So plot VL versus IS. So your plane here. So your VL is blue color 26.6. Okay. So this one is your VL. And your IS is 0.89 negative 63.4. So negative 63. So I think this one. So this one is your IS. The angle is negative 63.4 degrees. Okay, what I want to highlight here, as you can see, the voltage and the current that flow inside an inductor is still remain the same in terms of the in terms of the angle. As you can see, the voltage, the current will always lagging the voltage. Okay, and the angle is 90 degrees. The total is actually 90 degrees. Okay.
Doctor,
Yeah.
for the leading and lagging, we should write I first or we first?
Usually I, because usually in standard, okay, TNB standard, in power system standards, in electrical engineering standard also, when we said about leading and lagging, automatically we say that, oh, that lagging meaning that the current is lagging. Okay,
Okay, Doctor.
because in a standard form, for example, in electrical engineer TNB power system, when we discuss about leading and lagging, so they just say, oh, the this is a leading power factor system, this is lagging power factor system. So meaning that lagging is actually always referring the current first. The current is lagging the voltage. So when we talk about lagging, so the current will come first. So meaning that we are referring to the current. Okay, that is the standard actually. The standard in yeah, during the study, also during my undergraduate study, so quite confused. Okay, which one is leading, which one is lagging, why, but there, but is it actually because of the standard? We are, when we talk with an engineer, so when you say about leading and lagging, so automatically they will actually say that when you say about lagging, so the current will come first. Current is lagging the voltage. The wording. Okay. Because in electrical power system, they are what we call power factor, lagging power factors, leading power factors. So that is actually, when you say about lagging power factors, so actually that one is the current is lagging the voltage. So lagging is actually referring to the current. Leading meaning that the current is leading the voltage. Okay. I hope that answer your question. Okay, so I want to highlight that this one, if actually if we look at the relationship of the voltage and the current at particular elements, for example, resistor, yes, the voltage and the current relationship, as you can see, are in phase. And if you look at the relationship of the voltage and the current that flow inside an inductor, you will see that the current will always lagging the voltage by 90 degrees. But when we see the total, what is the relationship of the voltage and current of the total impedance? Yes, this one is not 90 degrees, or this one is not 90 degrees anymore. Okay, so this one is actually referring to the first one. So this one is actually, we can see that the effect of the impedance we see here. Okay, but when we look at the particular elements, for example, resistor, this one, inductor is this one. Okay, but the total here, which is R plus JXL, then you need to use this one, referring to this phasor lah. Okay. So if you are being asked to sketch the phasor for VS and IS, so just use you need to You calculate first the VS, sorry, and then VS here is given. You calculate the IS. Okay, then you just plot. You just plot. Okay, whatever that you have calculated, you just plot. So don't, I think don't make it because if you, itulah sometimes quite confused kan. But just plot. Okay, you calculate first and then you plot. Okay, and then after that, after you plot, then you baru you think about the logic lah. Okay. For example, at this point, this is inductive load. So meaning that the current, the total current that you calculate must always lagging the voltage by some degrees of phase. Okay. And then for the second question, this one is particularly actually to sketch the voltage across these particular elements, which is resistor. So when you say about particular element R, so meaning that the voltage and the current should be in the same phase, okay, which has been shown here in phase, okay. And then when it require you to sketch what is the voltage and current that flow inside this inductor, the relationship of the voltage and current across the inductor must be, the current must be lagging the voltage by 90 degrees. Okay. Okay, I think that's all from me for this online class. And please watch the pre-recorded videos, which is, I think I have shared with you 3 examples for this basic Ohm's law of the AC circuits. And by by Wednesday, we will, I think, no online class. Okay, no online class, meaning that you need to watch the pre-recorded video of the nodal and mesh analysis. Okay, it's actually the same concept actually. Okay, the same concept. There is no different. The only difference is actually right now you are involving with the complex numbers. Okay.
Doctor,
And yeah. Sorry.
Wednesday or tomorrow?
Oh,
Or
sorry. Tomorrow, yes, tomorrow.
okay.
Yes, tomorrow. So tomorrow, no online class. So you, I will share the link. I think on tomorrow. Tomorrow I will share the link. You just watch it. Okay.
Doctor,
So yeah.
in all classes now pre-recorded, right?
Yes.
Yeah, okay.
Yes.
So
Some
tomorrow,
of the will be
tomorrow no class.
pre-recorded. So tomorrow, no online class.
Okay.
Okay. So you just watch. So after this, just watch the examples of this basic Ohm's law. I have 3 examples. And then tomorrow I will share the link of the pre-recorded video for the nodal and mesh analysis.
Doctor, now we are in AC, right?
Yes, right now we are in AC circuit.
Why we are studying mesh now and nodal?
Okay, because even though it is similar, but there are some, it's like a mathematics. You need to do some exercise. Okay? You need to do some exercise to familiarize the complex numbers, how you deal with the simultaneous equation with the complex numbers.
You mean, Doctor, nodal analysis in terms of complex and AC circuit, right?
Yes, yes,
okay.
complex numbers, yes.
Okay.
Yes.
Okay, noted.
Okay, so I think that's all from me. Thank you very much. See you tomorrow. See you next week, I think. Okay. Thank you. Assalamualaikum and have a very good day.
Walaikum salam.
Waalaikumsalam, doctor. Thank you, doctor.
Okay.
Thank
you, doctor.